In the last video, we started with a cube and we constructed an icosahedron. I'll leave a link to that video in the description. Okay, so what we did was we put center face dots here and here. This is the front left face, and here back face, and here is a front face center dot, and here in the back center dot, and over here, let's take a different color, top and bottom center face dots. So what we did was draw golden rectangles through each of these center dots. There's one golden rectangle. This is through the top and bottom center dot. Now we take another pair of center dots and we do another golden rectangle, but in a perpendicular direction. And here we've finished it off. We've got 3 perpendicular golden rectangles, and we take the edges of the golden rectangles, all 12 of these edges, and we connect them in the way I described in the last video, and we get an icosahedron. There's our finished product. Very beautiful thing, an icosahedron. So this was the construction we did in the last video, but the question is, why does this work? So each one of these rectangles looks like this. This is side length 1, and this was 1/5, the golden ratio, as you recall from last video. And when we divide long divided by short side, we have 1/1/5, and that's pi. So this thing is indeed a golden rectangle, and we have 3 of them here. 1, 2, 3. This is the third one. Okay, so why does this work? That's a very good question, and let's look at it from the point of view of geometry, and it's very, very interesting, I think. The first thing to think about is this. This icosahedron object is quite complicated to look at. It's just a bunch of lines. It looks really hard to understand, but it's much easier to understand when we think about the following idea. There are two types of edges, and this is an idea that will help you to visualize everything that's going on. Okay, so let me make some room here. Let me show you what I mean by 2 types of edges. So here are the sides of my golden rectangle. These are the vertices of my icosahedron. So I've got the sides of the 3 golden rectangles. And let's label some things. Call this A, this B. No, we'll call this D and E. Will be consistent with what I will do in a few minutes. Okay, so what we have are 2 different types of edges. This is one kind of edge. So DE, we'll call this a side edge. A side edge. And what do I mean by side edge? Well, this lies entirely on one side of the cube. That's this edge here. However, this edge from A to D, well, let me use a color for that. Hang on. This edge from A to D, this is different. Okay, AD, we'll call this a diagonal edge. All right, so DE lies entirely in one side of the cube, DE. But AD is not like that. AD touches 2 adjacent sides of the cube. See, A is on this side and D is on this side of the cube. So they're qualitatively different types of edges. Okay, now here's an interesting theorem. All the side edges are congruent. I'm sure you can argue why that's easy, because they're the sides of the 3 golden rectangles, and since this is a unit cube and all the sides of the unit cube are the same, okay, by symmetry this is true. But we also have this. all diagonal edges are also congruent. So they're all the same. So AD is the same as, for example, let's try this one. This edge from D to this point here, they are equal. They don't look equal here because of the perspective, but they have to be equal. And why is that so? Well, from symmetry. But I want you to do it as an exercise. So as an exercise, try to give me an argument why these two classes or categories of edges are equal among themselves. All right, but we have to now prove that all of them are equal. That is, all of the side edges are equal to all of the diagonal edges. That's the way to prove that this thing is a regular icosahedron and that this construction works. So here's the strategy. Here's the brilliant strategy. So all we need to do is we take one side edge somewhere, okay, and then we take one diagonal edge somewhere, and if we can prove that those two are equal, then all sides of the icosahedron will be equal because of this, okay? And so we're going to do it for AD and DE. E.g., we will show this, show that AD, this diagonal edge, is equal to DE, this side edge. That's sufficient to prove that this construction works. And we'll find a condition. When is this true? Okay, so I added some construction lines here. I extended this side, this golden rectangle side, by AB. Then I draw a perpendicular here from B to C. C is the midpoint of the face. And let's call this distance U from C to, this was D and this is E. I won't be using D and E yet, but this is to define U. And I can put this here too. This is U. This is the midpoint of the face. Okay, so let's try to find, our first job is to find AC, this length from A to C. Well, okay, we've got, this is 1, the side of the cube is 1. We've got 2 U's here and 2 AB's. There's an AB here and there's another length AB here. So AB plus 2U plus AB has to add up to the length of the side of the cube. So now I have the length AB. Okay, that's good. Now BC, that's easy. That's because this is 1 and C is a midpoint. This is just 1/2. So BC is 1/2. Very good. And now I use Pythagoras' law. AC squared plus AB squared is, oh, wait a minute. That should be BC squared. Okay, very good. Now I solve for AC. I get this, and now I just do some simple algebra. And I get this. And this is my solution for AC. So I'm doing well. I have all 3 sides of this triangle ABC solved. Let's make some room here. Okay. Now consider this other triangle that I have here, triangle ACD, triangle ACD, over here in green. Well, this is a right angle. I'm sure you can see why. Maybe as an exercise you can argue why that's a right angle. So triangle ACD, the green triangle, is a 90-degree right triangle. And so I can use Pythagoras' law to find AD, the hypotenuse. I know AC from up here. We just solved for AC. And what is CD? CD is U. And so I get this, and with some simplifications, I get this. Okay, that's really good, because now let's look at what we have here. Okay, I'm done with AC. I don't need AC anymore. I have what I want. Let's ponder this for a second. Okay, I have AD. AD, this is a diagonal. edge. And I have my side edge, DE. What's the length of DE? Well, that's U and that's U, so the length of DE is 2U, and this is a side edge. So I'm ready to begin my final analysis. As we argued before, if any side edge such as DE is equal to any diagonal edge such as AD, then what happens is all edges are equal, all are congruent, and that gives us what we want, which is a regular icosahedron. This is exactly what we want. Okay, so this equation is the key to everything, but I want to get rid of this troublesome root, so let's square both sides. And this leads to the following equation. Okay, very nice, but we're not done yet. We can simplify this further. And we get this beautiful polynomial here, quadratic. And this is starting to get really exciting because now I can solve for u. I get two solutions. The first one here is no good because it's negative. So this is the solution that I want to keep. And now it remains to interpret what does this mean? Well, okay. Golden ratio is 1 plus root 5 over 2. So 2 phi is 1 plus root 5 over 1, like that. Okay, so let's multiply u times 2 phi and see what happens. Minus 1 plus root 5 over 4 times 1 plus root 5 over 1. And look at this magic, man. Look at this. Look at this. When these two multiply together, well, this is a difference of squares. So I get 5 minus 1. 5 minus 1 over 4, and that's 1. So what does that mean? Well, it means this, that u is the inverse of 2 phi. So u is 1 over 2 phi. Amazing. Very beautiful. We did it. Okay, so the side length DE is 2u, remember that, and that's 1 over phi. Okay, so we get the regular icosahedron exactly when the side length is 1 over phi. So the regular icosahedron, it magically happens when the side edges are 1 over phi, and this is exactly what we did in the last video and what we did above in this video when we had a rectangle of 1 and this side 1 over phi. This is a golden rectangle, and we had 3 of these, and those gives us all the side edges of the regular the icosahedron, and of course then because of this we get all the diagonal edges equal also. Okay, I want to explore one last thing, which is a very interesting thing. And that is what happens when u is not exactly equal to 1 over 2 phi. If you look at the figures in this video, you can see that u can be anywhere in this range from 0 to 1/2. As a simple exercise, you can try to justify this. So I'm going to take u to be closer to 0 and draw some figures and show you what it looks like. There, clearly not a regular icosahedron, a very strange looking thing with irregular sides, but still has some kind of cool symmetry to it. Just look at these interesting features here. You've got these triangular pieces that are really thin, and you got some triangular pieces that are much bigger. Okay, let's try u is closer to 1/2 now. I get the following. There you go. Very interesting objects and quite different from what we've seen above, from anything I've ever seen before, actually. Very, very interesting. Well, that's it for our icosahedron studies. There's more that maybe I'll do in the future. There are some very interesting properties of platonic solids. I think that studying and doing problems with 3D geometry and 3D figures is very mind expanding in a way that maybe other activities is not. So it's not like normal geometry. One of the problems with 3D geometry is that it really helps if you have some kind of software to do the drawings. And I use Asymptote to do these drawings, which is pretty good. There are other things you can try, like PyVista or something. But Asymptote is okay. And it opens whole new worlds of thought and is good for making your mind sharper. So if you like this video, if you like platonic solids, then comment and, of course, subscribe. And I will see you next time.